Section 1.2, Units and Standards. Learning Objectives. By the end of this section, you will be able to 1. Describe how SI base units are defined. 2. Describe how derived units are created from base units. 3. Express quantities given in SI units using metric prefixes. As we saw previously, the range of objects and phenomena studied in physics is immense. From the incredibly short lifetime of a nucleus to the age of Earth, from the tiny sizes of subnuclear particles to the vast distance to the edges of the known universe, from the force exerted by a jumping flea to the force between Earth and the Sun, there are enough factors of 10 to challenge the imagination of even the most experienced scientist. Giving numerical values for physical quantities and equations for physical principles allows us to understand nature much more deeply than qualitative descriptions alone. To comprehend these vast ranges, we must also have accepted units in which to express them. We shall find that even in the potentially mundane discussion of meters, kilograms, and seconds, a profound simplicity of nature appears. All physical quantities can be expressed as combinations of only 7 base physical quantities. We define a physical quantity either by specifying how it is measured or by stating how it is calculated from other measurements. For example, we might define distance and time by specifying methods for measuring them, such as using a meter stick and a stopwatch. Then, we could define average speed by stating that it is calculated as the total distance traveled divided by time of travel. Measurements of physical quantities are expressed in terms of units, which are standardized values. For example, the length of a race, which is a physical quantity, can be expressed in units of meters, for sprinters, or kilometers, for distance runners. Without standardized units, it would be extremely difficult for scientists to express and compare measured values in a meaningful way. Figure 1.7. Figure 1.7. Distances given in unknown units are maddeningly useless. Two major systems of units are used in the world. SI units, for the French Système International d'Unités, also known as the metric system, and English units, also known as the customary or imperial system. English units were historically used in nations once ruled by the British Empire and are still widely used in the United States. English units may also be referred to as the foot-pound second, FPS, system, as opposed to the centimeter-gram second, CGS, system. You may also encounter the term SE units, named after the Society of Automotive Engineers. Products such as fasteners and automotive tools, for example, wrenches, that are measured in inches rather than metric units are referred to as SE fasteners or SE wrenches. Virtually every other country in the world, except the United States, now uses SI units as the standard. The metric system is also the standard system agreed on by scientists and mathematicians. 1.2.1 SI units. Base and derived units. In any system of units, the units for some physical quantities must be defined through a measurement process. These are called the base quantities for that system and their units are the system's base units. All other physical quantities can then be expressed as algebraic combinations of the base quantities. Each of these physical quantities is then known as a derived quantity and each unit is called a derived unit. The choice of base quantities is somewhat arbitrary, as long as they are independent of each other and all other quantities can be derived from them. Typically, the goal is to choose physical quantities that can be measured accurately to a high precision as the base quantities. The reason for this is simple. Since the derived units can be expressed as algebraic combinations of the base units, they can only be as accurate and precise as the base units from which they are derived. Based on such considerations, the International Standards Organization recommends using 7 base quantities, which form the International System of Quantities, ISQ. These are the base quantities used to define the SI base units. Table 1.1 lists these 7 ISQ base quantities and the corresponding SI base units. ISQ base quantity. SI base unit. Length. Meter, m. Mass. Kilogram, kilogram. Time. Second, s. Electrical current. Ampere, A. Thermodynamic temperature. Kelvin, K. Amount of substance. Mole, mole. Luminous intensity. Candela, CD. Table 1.1. ISQ base quantities and their SI units. You are probably already familiar with some derived quantities that can be formed from the base quantities in Table 1.1. For example, the geometric concept of area is always calculated as the product of two lengths. Thus, area is a derived quantity that can be expressed in terms of SI base units using square meters, m, multiplied by m equals m square. Similarly, volume is a derived quantity that can be expressed in cubic meters, m cubed. Speed is length per time, so in terms of SI base units, we could measure it in meters per second, meter per second. Volume mass density, or just density, is mass per volume, which is expressed in terms of SI base units such as kilograms per cubic meter, kilogram per meter cubed. Angles can also be thought of as derived quantities because they can be defined as the ratio of the arc length subtended by two radii of a circle to the radius of the circle. This is how the radian is defined. Depending on your background and interests, you may be able to come up with other derived quantities, such as the mass flow rate, kilogram per second, or volume flow rate, m cubed per s, of a fluid, electric charge, A. Dot, s, mass flux density open bracket, kilogram, over, open parenthesis, m squared, dot, s, closed parenthesis, closed bracket, and so on. We will see many more examples throughout this text. For now, the point is that every physical quantity can be derived from the 7 base quantities in Table 1.1, and the units of every physical quantity can be derived from the 7 SI base units. For the most part, we use SI units in this text. Non-SI units are used in a few applications in which they are in very common use, such as the measurement of temperature in degrees Celsius, degrees C, the measurement of fluid volume in liters L, and the measurement of energies of elementary particles in electron volts, eV. Whenever non-SI units are discussed, they are tied to SI units through conversions. For example, 1 liter is 10 to the power of -3 meter cubed. Check out a comprehensive source of information on SI units. https://openstaxcollege.org/l/21 SI-units closing parenthesis. At the National Institute of Standards and Technology, NIST, reference on constants, units, and uncertainty. 1.2.2. Units of time, length, and mass. The second, meter, and kilogram. The initial chapters in this textbook are concerned with mechanics, fluids, and waves. In these subjects, all pertinent physical quantities can be expressed in terms of the base units of length, mass, and time. Therefore, we now turn to a discussion of these 3 base units, leaving discussion of the others until they are needed later. A. The second. The SI unit for time, the second, abbreviated S, has a long history. For many years it was defined as 1/86,400 of a mean solar day. More recently, a new standard was adopted to gain greater accuracy and to define the second in terms of a non-varying or constant physical phenomenon, because the solar day is getting longer as a result of the very gradual slowing of Earth's rotation. Cesium atoms can be made to vibrate in a very steady way, and these vibrations can be readily observed and counted. In 1967, the second was redefined as the time required for 9,192,631,770 of these vibrations to occur. Figure 1.8. Note that this may seem like more precision than you would ever need, but it isn't. GPSs rely on the precision of atomic clocks to be able to give you turn-by-turn directions on the surface of Earth, far from the satellites broadcasting their location. Figure 1.8. An atomic clock such as this one uses the vibrations of cesium atoms to keep time to a precision of better than a microsecond per year. The fundamental unit of time, the second, is based on such clocks. This image looks down from the top of an atomic fountain nearly 30 feet tall. Credit: Steve Jurvetson. B. The meter. The SI unit for length is the meter, abbreviated m. Its definition has also changed over time to become more precise. The meter was first defined in 1791 as 1, over 10 million of the distance from the equator to the North Pole. This measurement was improved in 1889 by redefining the meter to be the distance between two engraved lines on a platinum iridium bar now kept near Paris. By 1960, it had become possible to define the meter even more accurately in terms of the wavelength of light, so it was again redefined as 1,650,763.73 wavelengths of orange light emitted by krypton atoms. In 1983, the meter was given its current definition, in part for greater accuracy, as the distance light travels in a vacuum in 1/299,792,458 of a second, figure 1.9. This change came after knowing the speed of light to be exactly 299,792,458 meters per second. The length of the meter will change if the speed of light is someday measured with greater accuracy. Light travels a distance of 1 meter in 1/299,792,458 seconds. Figure 1.9. The meter is defined to be the distance light travels in 1/299,792,458 of a second in a vacuum. Distance traveled is speed multiplied by time. C. The kilogram. The SI unit for mass is the kilogram, abbreviated kilogram. It is defined to be the mass of a platinum iridium cylinder kept with the old meter standard at the International Bureau of Weights and Measures near Paris. Exact replicas of the standard kilogram are also kept at the U.S. National Institute of Standards and Technology, NIST, located in Gaithersburg, Maryland, outside of Washington, D.C., and at other locations around the world. Scientists at NIST are currently investigating two complementary methods of redefining the kilogram, see figure 1.10. The determination of all other masses can be traced ultimately to a comparison with the standard mass. There is currently an effort to redefine the SI unit of mass in terms of more fundamental processes by 2018. You can explore the history of mass standards and the contenders in the quest to devise a new one at the website https://www.nist.gov/pml/productservices/redefining-kilogram of the Physical Measurement Laboratory. Figure 1.10. Redefining the SI unit of mass. Complementary methods are being investigated for use in an upcoming redefinition of the SI unit of mass. A. The U.S. National Institute of Standards and Technology's watt balance is a machine that balances the weight of a test mass against the current and voltage, the watt, produced by a strong system of magnets. B. The International Avogadro Project is working to redefine the kilogram based on the dimensions, mass, and other known properties of a silicon sphere. Credit A, and Credit B. Modification of work by National Institute of Standards and Technology. 1.2.3. Metric prefixes. SI units are part of the metric system, which is convenient for scientific and engineering calculations because the units are categorized by factors of 10. Table 1.2 lists the metric prefixes and symbols used to denote various factors of 10 in SI units. For example, a centimeter is 1/100th of a meter. In symbols, 1 centimeter equals 10 to the power of -2 meter. And a kilometer is 1,000 meters. 1 kilometer equals 10 to the power of 3 meter. Similarly, a megagram is 1,000,000 grams. 1 megagram equals 10 to the power of 6 grams. A nanosecond is a billionth of a second. 1 nanosecond equals 10 to the power of -9 s. And a terameter is 1,000,000,000,000 meters. 1 terameter equals 10 to the power of 12 meters. Prefix. Symbol. Meaning. Iota. Y. 10 to the power of 24. Zeta. Z. 10 to the power of 21. Exa. E. 10 to the power of 18. Peta. P. 10 to the power of 15. Tera. T. 10 to the power of 12. Giga. G. 10 to the power of 9. Mega. M. 10 to the power of 6. Kilo. K. 10 to the power of 3. Hecto. H. 10 to the power of 2. Deca. Da. 10 to the power of 1. Yocto. Y. 10 to the power of negative 24. Zepto. Z. 10 to the power of negative 21. Atto. A. 10 to the power of negative 18. Femto. F. 10 to the power of negative 15. Pico. P. 10 to the power of negative 12. Nano. N. 10 to the power of negative 9. Micro. Mu. 10 to the power of negative 6. Milli. M. 10 to the power of negative 3. Centi. C. 10 to the power of negative 2. Deci. D. 10 to the power of negative 1. Table 1.2. Metric prefixes for powers of 10 and their symbols. The only rule when using metric prefixes is that you cannot double them up. For example, if you have measurements in petameters, 1 petameter equals 10 to the power of 15 meters. It is not proper to talk about megagigameters, although 10 to the power of 6, multiplied by 10 to the power of 9, equals 10 to the power of 15. In practice, the only time this becomes a bit confusing is when discussing masses. As we have seen, the base SI unit of mass is the kilogram, but metric prefixes need to be applied to the gram, g, because we are not allowed to double up prefixes. Thus, 1,000 kilograms, 10 to the power of 3 kilogram, is written as a megagram, 1 megagram, since 10 to the power of 3 kilogram equals 10 to the power of 3 multiplied by 10 to the power of 3 gram equals 10 to the power of 6 gram equals 1 megagram. Incidentally, 10 to the power of 3 kilogram is also called a metric ton, abbreviated T. This is one of the units outside the SI system considered acceptable for use with SI units. As we see in the next section, metric systems have the advantage that conversions of units involve only powers of 10. There are 100 centimeter in 1 meter, 1000 meter in 1 kilometer, and so on. In non-metric systems, such as the English system of units, the relationships are not as simple. There are 12 inches in 1 foot, 5,280 feet in 1 mile, and so on. Another advantage of metric systems is that the same unit can be used over extremely large ranges of values simply by scaling it with an appropriate metric prefix. The prefix is chosen by the order of magnitude of physical quantities commonly found in the task at hand. For example, distances in meters are suitable in construction, whereas distances in kilometers are appropriate for air travel, and nanometers are convenient in optical design. With the metric system, there is no need to invent new units for particular applications. Instead, we rescale the units with which we are already familiar. Example 1.1. Using metric prefixes. Restate the mass 1.93, multiplied by 10 to the power of 13 kilogram using a metric prefix such that the resulting numerical value is bigger than 1 but less than 1000. Strategy. Since we are not allowed to double up prefixes, we first need to restate the mass in grams by replacing the prefix symbol k with a factor of 10 to the power of 3. See Table 1.2. Then, we should see which two prefixes in Table 1.2 are closest to the resulting power of 10 when the number is written in scientific notation. We use whichever of these two prefixes gives us a number between 1 and 1000. Solution. Replacing the k in kilogram with a factor of 10 to the power of 3, we find that 1.93 multiplied by 10 to the power of 13 kilogram equals 1.93 multiplied by 10 to the power of 13 multiplied by 10 to the power of 3 gram equals 1.93 multiplied by 10 to the power of 16 gram. From Table 1.2, we see that 10 to the power of 16 is between peta, 10 to the power of 15, and exa, 10 to the power of 18. If we use the peta prefix, then we find that 1.93 multiplied by 10 to the power of 16 gram equals 1.93 multiplied by 10 to the power of 1 petagram, since 16 equals 1 plus 15. Alternatively, if we use the exa prefix, we find that 1.93 multiplied by 10 to the power of 16 gram equals 1.93 multiplied by 10 to the power of negative 2 exagram, since 16 equals negative 2 plus 18. Because the problem asks for the numerical value between 1 and 1000, we use the peta prefix and the answer is 19.3 petagram. Significance. It is easy to make silly arithmetic errors when switching from one prefix to another, so it is always a good idea to check that our final answer matches the number we started with. An easy way to do this is to put both numbers in scientific notation and count powers of 10, including the ones hidden in prefixes. If we did not make a mistake, the powers of 10 should match up. In this problem, we started with 1.93 multiplied by 10 to the power of 13 kilogram, so we have 13 plus 3 equals 16 powers of 10. Our final answer in scientific notation is 1.93 multiplied by 10 to the power of 1 petagram, so we have 1 plus 15 equals 16 powers of 10. So, everything checks out. If this mass arose from a calculation, we would also want to check to determine whether a mass this large makes any sense in the context of the problem. 1.1. Check your understanding. Restate 4.79 multiplied by 10 to the power of 5 kilogram using a metric prefix such that the resulting number is bigger than 1 but less than 1000.